Now, what is happening here? Let us see this. What is happening here? So let me first write the equation that I wrote for that. This is T minus D minus, because of this wheel in contact with the surface, the landing gears, I say net frictional force is Ff, and let's see, the ground reaction is R and weight is W. So one thing I know, that here, let me complete this, L plus R equal to W, or R equal to W minus L. Naturally, if lift is equal to weight, then R will be 0. Okay? This I know. So if I now write this, complete this equation, I have T minus D minus Ff is equal to M into A. And for Ff, I can write equal to mu into R, that is mu R. I am purposely introducing R for rolling friction coefficient, and for R I am writing W minus L. So now what this equation transform into? T minus D minus mu R into W minus L equal to, let me write it here, equal to M A, or I can write W by G into A. You could see here, this term, the drag and L, both drag and L changes with V square. And this airplane is accelerating from 0 to V, which is V takeoff. That means each point, since the velocity or the speed is changing, this net force acting on the aircraft is also changing. It is not constant as it was here. Correct? That is the problem now. Now the acceleration, if you see, if I write acceleration, it will be G by W T minus D minus mu R W minus L. That's all. Okay? What is this W here? This W is nothing but W takeoff, because we are on the ground. As I am climbing and climbing, after 1 hour or a finite time, half an hour even, you will find the weight has reduced because the fuel is consumed. So this W takeoff is the net gross weight. Okay? So if this is the acceleration, now how do I solve this problem? But we have learned from class 6th or 7th standard, if the acceleration is somehow constant, somehow if I can assume it's the average acceleration will work for this, then I have to only recall my 6th, 7th standard knowledge to solve this problem, and we will be doing exactly that. Okay? What is found is, if I compute this thrust which changes with speed, drag, lift, all this term, if I compute at 0.7 times V takeoff, is it clear? If I compute this term, thrust, which changes with speed, may not be very appreciable, but it does change. Drag, you know, yes, V square, lift V square. So actually, as the speed increases, this term will go on changing, hence the acceleration will not remain constant. But what is found is, if I compute drag and lift and try to give a correction for thrust at 0.7 V takeoff, that is, as if it is moving with an average acceleration, which can be assumed to be constant, evaluated at 0.7 V takeoff. That means what? I will calculate drag at 0.7 takeoff, I will calculate lift at 0.7 takeoff, and I will do thrust correction for 0.7 V takeoff. If It is required. You can, for all practical purpose, you can assume thrust is not varying. Okay? Drag and lift, that is the primary thing here as far as causing the acceleration is concerned. So what is learned? Very simple, that though this acceleration is changing, however, if I calculate this lift and drag at 0.7 v takeoff, I can assume this is the average acceleration and good enough to calculate this SG, v equal to 0 to v equal v takeoff. I call this distance SG. So now tell me, if A is A average, evaluated at 0.7 v takeoff, then what is the problem? Then simply I go for this v square minus u square equal to 2as. I know initial velocity is 0, so I know s square equal to v square by 2a. So I know s equal to v square by 2a, and that is nothing but my SG. To be more precise, SG I can write as v takeoff square by 2a evaluated at 0.7 v takeoff. Very simple. You see how good it is if your concepts are a little bit clear in class 6th, 7th or 8th, right? Okay, now we'll put the expression and see what additional information we get out of this. Please remember, whenever we write anything in the blackboard, whatever equations we are writing, finally our design eye is back in our mind. We'll try to extract maximum information so that I can incorporate those understanding in designing an aircraft. Otherwise, it is just like writing some equations. Okay? So SG now, once I substitute v takeoff square by 2a, and what was v takeoff? It was 1.2 times v stall. So this was 1.2 times v stall was 2 w by s rho CL max. So if I now put it here, what will happen? I'll just get an expression SG equal to, let me write the expression, 1.44 W by S takeoff by G rho CL max T by W takeoff minus D by W takeoff minus mu r into 1 minus L by W takeoff. So this is W minus L, so that's divided by W, so it has come like this. I'm sure you will be able to derive this expression. You have to just substitute for V takeoff this expression, and for A you have to put the average acceleration. So I will write this evaluated at point V takeoff. Okay? I will check that whether you are doing these small derivations or not through assignments. Please do that because this will give you insight. Okay? As I was mentioning, do you think the whole effort for calculating SG is over here? Let us see or visualize one thing. So far, whatever aerodynamic characterization we have done, that is estimation of CL, estimation of drag puller, understanding about downwash, all those things were when the aircraft was flying in air, far away from the ground. Now imagine when this airplane is taking off from the ground, so these wings are very close to the ground. So what will happen? those wingtip vortices which is being generated while it is taxiing or accelerating on the runway, these wingtip vortices will now go and interfere with the ground and their strength will be reduced. For knowing the details about why this is being reduced, you can read any book on aerodynamics. But please understand from a flight mechanics point of view, near the ground, when the airplane is going like this for takeoff, because of presence of ground, these wingtip vortices, their strength gets reduced and the induced drag, KCL square component, also gets reduced. Further, the downwash also goes to little lesser in magnitude. Okay? So that means if I want to compute the drag, I need CD naught plus KCL square, the drag puller that to be used, because I will multiply this with half rho v square s. That will be my drag when it's going for a takeoff. But I know because the wing is too close to the ground, the wingtip vortices will interfere with the ground and there will be reflection and the wingtip vortices will lose their strength. So the induced drag component will be less. So I cannot really use CD naught plus KCL square. So what is used is CD naught plus phi KCL square, and this is half rho v square s. So this phi, number wise, if you take induced drag is around 80%, 70 to 80%, good enough. That means 20 to 30% reduction is there. Okay, 20% is fairly a good initial design approximation, but there are many researchers' effort given this value phi, given an expression to estimate phi for incompressible flow, and that is modeled as 16h by b. I will explain you what is this, plus 1 plus 16h by b whole square, and this value is less than 1. What is h? H is the distance of the wing from the ground. This is the h, and b is the span. B, you know, is the span, right? If it has flown 2 to 3 times the span vertically, then ground effect should not be taken at all. Okay? So what is the new addition thing we have done? We know because of ground effect, I am calling that a ground effect. Again I repeat, very loosely or very, what do you call, I am not going deep into it. The ground effect, the flight mechanism, I will tell, in this case is the wingtip vortices which were generated when the airplane is accelerating and generating lift. These wingtip vortices will interfere with the ground, there will be reflection, and the strength of wingtip vortices will reduce, reducing the induced drag. Okay? And that is modeled through phi. So this is one change you need to have. Another question comes, when airplane is going like this and start taking a turn like this, we call rotate like this, how much time it will take, how much time is allowed to rotate the airplane? For all practical purpose, it's not more than 3 seconds. So rotate, then transition, this whole, sometime for a high T by W aircraft, you may find they're happening one time. They're going like this. You won't be able to distinguish. Okay? But we need to cater for those. So coming back here again, once I know this, how to calculate, and sometimes you will find many literature, there is a advice. When you're calculating the lift, don't take the CL max, you take 0.8 times the CL max. Okay? So for CL, you take it, CL takeoff, you take it as 0.8 times CL max. All this nitty-gritty will be clear once you solve a numerical problem. But now this session is to understand the physics behind it. Okay? All these numbers have come not necessarily because of well understood physics, but it is from the regulatory angle also to ensure that everything is safe. Okay. Now we'll come back here and try to give an interpretation to this SG, and from the designer's eye we'll try to get some inference. What do I see? I see SG is proportional to W by S. Okay? That is, if wing loading is less, SG is less. Wing loading is less means large wing. But the problem with large wing is, large wing means large drag. So there is a conflict. So designer has to see how do I handle this. And you will see that is why high-speed airplane, they do not want very high span wings. They are low span wings, low aspect ratio wings. By now you understand. Okay. Then also we see that SG, if you carefully see, if I take this WTO, W takeoff on the top here, right, then actually SG will be proportional to W takeoff square. What is the message? The message is, if the weight is increased, heavier aircraft will have larger SG. That means they require larger ground roll distance to achieve V takeoff. So the moment you want to design a heavier aircraft, you should be careful. It will demand larger ground roll distance. Okay? But as a designer, you cannot keep quiet. You have to handle this situation. Larger aircraft, but not so large takeoff distance or ground roll distance. Loosely, what is the option? Option is increase CL max, use all high-tech innovative flaps, let the drag increase, we'll handle it, but let CL max increase. More than CL max, if you see, T by W, okay? This SG if we have an engine whose T by W is very high, that will help in reducing the SG distance, that is ground roll distance, which is also obvious. If I have got a very thrust efficient engine, the acceleration will be faster because T by W is high, so SG will be less. And finally I come to density. You see, it is inversely proportional to density of air from where you are taking off. As I was mentioning, from here you could see that very clearly. As density decreases, SG increases. That is, if we are going higher altitude airport, let's say Jammu Kashmir, let's say Leh Ladakh, where density of air will be less, so you will require larger ground roll distance. Okay, it's extremely important. Also, you understand from here that density not only changes with altitude, density also changes with whether it is a winter season or a summer season. Okay, so let us see for winter and summer season how SG will get affected. Now we'll try to have a closer look on this density aspect. Let us see, for simplicity, we assume that this term is more dominating than the rest of this term, which is not a very bad assumption. Okay, so I neglect this term compared to this term. After doing this approximation, I can write SG as 1.44 W takeoff square by G rho CL max into T. We also know the thrust varies with density. So in effect, here there is density variation, here there is density variation. So I can write SG varies inversely with rho square. Just not rho. Earlier we were talking about rho density. It is actually more than that. That is why you will find if you are trying to take off in hot summer days, then the density of air will be less, so you will be requiring larger SG. In a winter session where density of air is more compared to summer season, you will find SG will be less. And reverse happens in the winter season for the same aircraft or the same location of the airport from where we are going to take off. Clear? This is a very important understanding that if I have to reduce Hg, message is increase CLmax, reduce wing loading, increase T by W. These are the primary parameters which a designer will keep in mind. Okay? Now SR, which is rotation distance, and STR, which is transition distance, and SCL, which is climb distance. Climb distance. Let me complete here, distance. What are all this? We know that airplane starts from here, come to a stage where it is V takeoff, then rotate the airplane for 3 seconds, then there is a transition where he tries to arrange for climb. So this is SR, this is transition STR, and then there is a climb which is 15 meter. Okay? We are trying to find out SR first. Since we know it is at the most for 3 seconds, and this time also it is moving with V takeoff, so SR is very simple. SR is 3 seconds into V takeoff. Job is done. Okay? Now during transition, what happens? During the rotational phase, the nose wheel goes up and still moves with V takeoff like this. Then there is a pull-up type thing, slight pull-up. And during this pull-up, the pilot also adjusts himself, all the controls for a climb, ready for a climb, because he has to adjust those controls. So this part is best modeled as a pull-up with a radius of R. Okay? And this is a climb, so this is theta climb angle CL. Is this part clear? This, during rotation, the airplane was going like this. As it attains V takeoff, it rotates. That is, nose wheel will now leave the ground, still moving forward, and started going up. And there is a transition like this, during which the pilot adjusts itself for a climb preparation. So this part is for 3 seconds. So SR is 3 into V takeoff, and this part is part of a pull-up maneuver. We'll find out, and this is a straight climb. Okay. With this understanding, with little bit of geometry, we'll find out this distance. To calculate STR, we'll again see here, the assumption is, here it is V takeoff, and it is following a pull-up with radius R, and we know by now that for a pull-up, if this is L, this is W, then L minus W equal to M V square upon R. And if I divide by W, I get L by W minus 1 equal to M by W V square upon R, and this is equal to V square upon R G. So I get an expression N equal to 1 plus V square upon R G. What is the message? Message is, if I know some assessment of the value of load factor N, during which it was just doing a pull-up, and since I know V as V takeoff, I know G, so I should be able to get the value of R, and then use geometry, I should be able to get the value of STR. Okay? So to have an assessment of N, what is N? N is lift by W. When it is going for a takeoff, what we know? A lift is half rho V takeoff square SCL, and W I write here. What is V takeoff? V takeoff is 1.2 times V stall. And what is W? W I can write as half rho V stall square S into CL max. Correct? W is, by definition of V stall, is half rho V stall square S CL max equal to W. V takeoff I know 1.2 V stall, and this velocity or speed is V takeoff square, and here I write CL. And now try to find N, as we have assumed that during the takeoff the CL is 0.8 CL max. CL takeoff is 0.8 CL max. Then checking that expression I get N equal to half rho V takeoff is 1.2 into V stall square SCL is 0.8 CL max, and divided by W, W I know half rho V stall square S into CL max, because that is how V stall is defined. If I see now this ratio, I will get N equal to 1.2 square into 0.8, which is roughly equal to 1.15, just 15% more than situation N equal to 1. So what is the message? Message is, now you know what is N, you know what is V takeoff, find out R. So what will be R? So now R will be V takeoff square by 0.15 G. So please see that. By doing this approximation, we know the value of R. Okay? Now I have to calculate STR. This is important. Using this expression of R. To get the value of STR, we will now do a little explanation, use the help of geometry. You know, by now you are all expert. Rate of climb, that was defined as V takeoff sine theta CL. Actually, I am using here theta CL. To be more precise, I will prefer to write it as V takeoff into sine gamma CL. Because for us, gamma is the flight path angle. Okay? If you see in textbook, they sometimes use theta CL. I am not writing theta CL, I am cutting it here. I will write V takeoff into sine gamma CL to give a stress that for flight path angle, we are using notation gamma, not theta. Theta is for the pitch orientation. Okay? Attitude of the airplane respect to the ground. Gamma is the angle between the velocity vector and the horizon. So this will be equal to V takeoff by now sine gamma CL is T minus D by W for an unaccelerated climb. This is for, do you remember that? Do you want me to repeat? Straight climb. How it came? Let us revisit, and so that you do not flip further files. Remember, this is the airplane which is going with a velocity V. This is W. This is the gamma flight path angle, not theta, gamma flight path angle. So what we can write, T minus D is here, D minus W sine gamma is equal to 0 for an unaccelerated climb. This is unaccelerated climb. So from here I write T minus D by W is equal to sine gamma. Right? So for sine gamma climb, I have written this expression. Our aim is to find out STR, and STR is nothing but R sine gamma CL, And from this expression, you can find out sine gamma CL is equal to T minus D by W. So I put sine gamma CL value computed from here in this expression. R I have already found out, so I can find out what is STR. If I repeat again the last part, please understand that STR is approximated as R sine gamma CL, and sine gamma CL I have calculated using T minus D by W. R we have calculated assuming pull-up. Already I have shown that. So once I know this number, I have no issues. Finally, we are left with, this is gamma CL. Many books will write it as theta CL. And to find out this distance, which is SCL, okay? And you know, there was a pull-up, there was a roll, and like this. And let's say this distance is from the ground. Let this distance be HTR. So I can easily find out SCL by using this relation, SCL equal to 15 minus HTR by tan gamma CL. If HTR greater than 15 meter, then SCL equal to 0. This is simply by this geometry, because you know this is the total height is 15 meters. It is as simple as that. I hope you should be able to do this yourself. Okay? So once you calculate all these segments, you add it up, you will get the takeoff distance. But the question comes, will you only keep that much of distance? Answer is obviously no, because midway the airplane can fail. The engine may stop. So you have to keep margin for that. So generally, you keep 100% margin. Okay? If takeoff length is 500 meter, you will keep around 1 kilometer runway. Right? Clear? Please keep this in mind if land is available. If land is not available, then you may put more stringent conditions. Thank you very much.